Okay guys, in this module we're going to discuss these two foundational concepts in physics, which are displacement and velocity. These are really sort of core foundational concepts that we'll build on throughout the course of the year. Displacement is a quantity that's very related to a more familiar concept, and that's distance. Velocity is a measurement that's related to the more familiar concept of speed. But they're a little bit different than distance and speed, and I think hopefully you'll understand why as we move through this video. So let's start with displacement. And this is rather than thinking about distance, or you could think of distance maybe as like the total ground an object covers. Displacement we're going to define as the change in an object's position. So change in the position of an object, which sounds an awful lot like distance, but I think you'll see in a minute here there's a crucial distinction. How could I write this? Well, position, if we were moving along an x-axis, you might call position x. If you were moving along a y-axis, you might call the position y, or z-axis z, so on and so forth. So the displacement is the change in the position, and we write change in with the Greek letter delta, which is this triangle. So I could write delta x, and this would be the displacement along an x-axis. Alternatively, it could be delta y, it could be delta z. If you were moving along a radius, for instance, if you were moving radially along a circle, you could call it delta r, etc. It could be anything. And the way we define this mathematically is we say that the change in the position, so I'll use delta x for now, we could say that delta x is equal to your final position, so that's xf, minus initial position x sub I. So these sub-indices, the f stands for final and the I stands for initial. And that is our mathematical definition of displacement. That is how you express change in position, position final minus initial. It's important that it's final minus initial, and that's critical for the reason that the sign we get over here, whether or not this is positive or negative, matters. So if your displacement is positive, you get a positive displacement by having your final position being bigger than your initial position, and you get a negative value by having your final position being smaller than your initial position. And I think you'll see that ends up being really, really important. So it can be positive or negative. You might hear me use this term, this is what we call a vector quantity. Vector quantities, for right now, that I call it a vector quantity. For right now, I want you to know that all that means is it can be positive or negative. Next chapter we'll look in a lot more detail at what a vector really is. So for right now, we just know it can be positive and negative. So let's investigate this a little bit more. Here is an x-axis. Ooh, that's a terrible x-axis. Here we go. That's a better x-axis. Here we are. And let's imagine we have some little particle who lives here on the x-axis, and here he is. He's going to start out at the origin. So this is x equals 0. So here's our little particle. And he starts off at the origin, and maybe he moves to this position over here. Maybe this is x equals 3. X equals positive 3 right here. So he has moved some displacement from 0 to 3, and so we could say, okay, well, what is that displacement? And I think it should be pretty clear here. The delta x is going to be the final position, positive 3, minus the initial position, which is 0, or just plus 3, which again, nothing too miraculous about that. We might like a unit in here too, by the way. Maybe this is meters. So positive 3 meters, maybe. So far, that looks a lot like distance, right? Well, the particle went 3 meters of distance, right? But here's where we might see a distinction between distance and displacement. Let's imagine after getting to x equals 3, maybe our little particle decides to go in the opposite direction and ends up now over here, right here. Let's say that this is x equals negative 2 meters along our x-axis. And then we could say, okay, well, what's the displacement now? What's the displacement? Well, it's final minus initial. So negative 2 minus 0. I'm thinking about the whole trip. okay? From 0 to +3 and back to -2. That's the entire trip that I'm thinking about. So the final position is where the particle ended up -2. The initial position was our starting position, 0. So what is this? This is -2 meters. And maybe now you can see why this is significantly different from distance, right? The distance the particle went wasn't -2. It was 3 plus 3 more to get back. That's 6 plus 2 more, 8. The distance traveled by the particle was 8 meters. But the displacement is -2 meters. So you can get a sense there for how they can be different. In fact, you could imagine the particle taking one more leg of the trip. Maybe after getting to -2, maybe the particle returns to x equals 0. And then what would the distance be? Well, it would be 3. The distance would be 3 plus 3 is 6 plus 2 is 8 plus 2 is 10 meters. But what would the displacement be? Well, the initial position is 0. The final position is 0. So the displacement in that case would be 0. So that's a quick introduction to displacement. Now, I mentioned we're going to talk about velocity as well. Let's get there now. Velocity is similar to speed, but there's a critical difference. Where speed you think of as the amount of distance covered per unit time, velocity is the amount of displacement per unit time. So it's the rate of displacement. And rate, when you see that word rate, think divide by time, right? That's what a rate is something changing over time. And so the way I can write this is the velocity, and we use v for velocity, is equal to the displacement, that's delta x, over the time, t. And I'm going to put in a third line up here to indicate that that's actually the definition of velocity. So that's our definition of velocity. The displacement per unit time. I didn't mention this before, maybe I should have. I used meters up here. We will generally in physics always use meters. In rare occasions we'll use something else, but almost always we're going to be using meters. And that's what we call the standard or SI unit for displacement is meters. So this guy up here is in meters. Time, our standard unit, is in seconds. So our unit here, our standard unit is meters per second. So get familiar with that unit. We'll use it quite a bit. So this is the displacement per unit time. You could imagine if we go back to our example of our particle here, we could throw in some sort of a time value. Maybe it took him I don't know, maybe it took him 10 seconds to get from 0 to +3. And then what would the velocity have been? Well, he went 3 meters, or +3 meters of displacement in 10 seconds, so that would be 0.3 meters per second. I think that's hopefully pretty clear. We'll look at that in a little bit more detail maybe in a minute. For right now, though, I should also mention, since our delta x is a vector, it can be positive or negative, velocity is also a vector, so it can be positive or it can be negative. Positive velocity means the object's moving in the positive direction. Negative velocity means the object is moving in the negative direction. Maybe this is a good time to indicate something here. I'm inclined to put a bar over that v. And that bar lets me denote that this, and you might have picked up on this already, that this velocity is what we call an average velocity. Average meaning it's the average velocity over some finite time interval, right? This delta t down here, this is a time interval, which means that over this time interval, the velocity may have changed a little bit, right? It might not have been constant. So for instance, if I said that I went, let's say I drove 120 miles, and let's say that I did that in, I don't know, let's say that I did that in 2 hours. You would say that, okay, well, your average velocity for the trip was 60 miles per hour, right? Well, does that mean I went 60 miles an hour the whole time? No, in fact, it's incredibly unlikely that I went 60 miles an hour the whole time, because I probably started not moving and sped up, and then I probably had to slow down at certain points and then speed up at certain points. So the 60 is an average of the entire trip. So this is an average velocity. There is such a thing as an instantaneous velocity, a velocity at an instant of time. We aren't going to really be able to deal with instantaneous velocities because if you look at the algebra here, if the time interval for this to be instantaneous, well, a mathematical instant is the time interval is equal to 0. And you can already see what would happen if I try to divide by 0. My calculator is not going to really like that very much. So it seems like for right now we can't really get an instantaneous velocity. There is a trick, but it involves calculus, and we're not going to deal with that this course. Okay, one last thing on since we're looking at velocity and displacement, I'd like to introduce a type of graph, a really important type of graph called a position time graph. So a position time graph is one wherein you have a vertical or y-axis, which is position. So I'll use x right now for position. Again, this could be y or z. It's the position along whatever axis you happen to be moving. And then on the horizontal axis, we have our time value, t. And you could plot the motion of an object along this on this graph. So maybe I'll do that. Maybe I'll say, like, what if I had an object moving in this way? What if here he is, and then we'll go like this. So that's our object moving, and I've sort of divided it into a few segments here. So let's call this first segment here, that's segment A. This is segment B, C, and D. So we have 4 different segments along the position time graph. And I'd like to think about what this graph is telling us. Well, if we think about it here, if we look at A, the object is clearly moving, right? The position is changing. And actually, maybe I should mention right away, it would be tempting to look at this graph. One big mistake would be to look at this graph and imagine that this object is moving in 2 dimensions, right? Because it looks like it's moving in 2 dimensions, right? It's moving up and down, and it's moving left and right. But remember, it's not. It's all this object is doing is moving along an x-axis. Remember, this axis is time. So the object is just going back and forth along an x-axis. So here, what's happening? Well, the object starts. In fact, maybe it would be helpful if I kind of drew my x-axis over here. Here's the x-axis that our particle is moving on. The particle starts at 0, so here's 0, and it moves in the positive direction, and maybe it ends up at, I don't know, let's call that 1. So it moves to x equals 1 in that first segment. That's part A. And then what does it do? Well, it seems in segment B like it just hangs out at position 1. In other words, it doesn't move, it stays there. And then what happens in C? Well, it continues to move. And you might be able to see that it seems to be moving quite a bit faster here, right? So maybe it goes all the way from 1 to, I don't know, 5. All the way out here. And if you look at the time intervals, right? The time intervals, here's our time interval for segment A. Here's the time interval for segment C, right? That's our time interval. And it looks like it moves a much bigger distance in roughly the same amount of time. So that seems to indicate that it's going faster. And in fact, it is. Okay, what happens in segment D? Well, in D, it seems to go backwards, right? It starts at 5 and ends up back at 1. So if it goes this way in C, then in D, it's coming backwards. In other words, it's a negative velocity. Now, some of you may have already picked up on the fact that this business about the slope indicating something about the speed is actually embedded right in this graph. So if I indicate, if I remember that the slope, m, remember m stands for slope, is the rise over the run, or the change in the y value over the change in the x value. Well, what is that in my graph? Well, my y value is position. So this is, my delta y is actually delta x, displacement. And my x value is t. Well, what is delta x over t? That's velocity. So in other words, on a position time graph, and this is always the case, the slope is equal to the velocity. So here I have a small positive slope, so I have a small positive velocity. Zero slope, zero velocity. Large positive slope, large positive velocity. Large negative slope, large negative velocity. So positive velocity, we could even go ahead and say this is positive velocity, this is zero velocity, this is a big positive velocity, and this is a big negative velocity. All right, so that's a quick introduction to position and velocity, and a look at a position time graph and how you can get velocity from a position time graph. We'll practice this quite a bit more in class, but that's it for now.